t'as dit quelque chose.
Il n'est pas content.
Ah, c'est pas configuré. Attends, tu as besoin de mon secret que on n'avait pas. Tu me donnes une minute. J'ai besoin d'une minute. Je dois aller sur YouTube.
Tu recommences à zéro?
Non, je dois aller sur YouTube. Si tu veux streamer sur YouTube, il faut que je te donne la clé. On n'avait pas fait.
D'accord. Bon, monsieur.
Oui, tu peux commencer. Moi, je.
It's our pleasure to have Vliet from École Normale, who is going to talk about bootstrapping the
to mechanics into account, but new avenues have been followed based.
Okay, sorry.
Yeah, okay. No, thanks very much for the invitation. I'm very happy to talk to you about a recent paper that I wrote with my wonderful collaborators Connor Bayan, Maria Nocchi, a PhD student in Oxford, and Eduardo Laudia, who is also in the audience here. And in this paper, we looked at the long-range Ising model from a point of view of the conformal bootstrap. So, both in the conformal bootstrap, but also more generally, the short-range Ising model is a model that's very well understood. So in 2 dimensions, it's exactly solvable, and in 3 dimensions, there's been a lot of effort to constrain it using the conformal bootstrap, and they've reached like very impressive high precision on it. But its long-range cousin, the long-range Ising model, remains much more mysterious, and that's why we wanted to revive this study of this model. And here, the long-range Ising model has not a single critical point that leads to a single CFT, but it actually has a line of fixed points parameterized by some parameter S that I will introduce in a minute. And so we can actually have a continuous set of non-local but unitary CFTs that we want to study. And just as the short-range Ising model is a very natural starting point for the study of local CFTs, we can say that the long-range Ising model is a natural starting point for non-local CFTs. And some examples are conformal defects, boundaries or interfaces or line defects, but also the study of QFTs in ADS. And even if you intrinsically maybe do not care so much about non-local CFTs, you might still want to have a better understanding of them because they might show up in the study of local CFTs using the bootstrap if you don't explicitly put in that they have to be local. So they can also be the theories that satisfy the bounds that you obtain, and that is another reason to understand why how they behave and what they look like. And of course, there's also maybe far in the future the idea that we could find such theories in nature or in certain models. But okay, I won't go into that any further. So for this talk, I will first give an introduction on the long-range Ising model and explain the physics behind it and some ways that you can look at it from a CFT perspective. And then I will introduce what's called OPE relations, which are relations between OPE coefficients that have proven to play a central role in our paper and put very constraining and are very constraining for the setup that we have considered. Then I will move on to the bootstrap, and I will in particular discuss the numerical bootstrap, and I will end with a conclusion. So the Hamiltonian of the long-range Ising is very similar to the short-range Ising one, with an interaction of 2 spin fields. with, of course, the main difference that now the interaction is long range, and its parameter and the exponents here are given by p, the dimension of the theory, and s, which is this parameter that I already shortly introduced, that parameterizes the line of fixed points that we have. And p, we will take it to be integer, and specifically I will discuss the case of p equals 2 and 3 and comment on p equals 1 at the end. But s can be non-integer.
But then S is between 0 and 1? I'm not sure.
Exactly. So S is, in this case, between p over 2 and, well, initially it was thought that it was bounded by 2 above, but it turns out that the interval is actually slightly smaller than that. And I will, in a minute, show what each of these ends of the interval correspond to in terms of a perturbative setup. So both of these sides of S, we can see it from a different point of view, perturbatively. And if we start on the lower end, we have S equals p over 2, and we can deform this by a small parameter epsilon.
Sorry, so is P related to the dimension of the
Yeah,
space?
P is the dimension
So
of the
P is
theory.
fixed.
Yes, yeah. So this is the fixed dimension. So indeed, for p equals to 2, this would be 1. And this is the starting point of the mean field theory. So we can define our action as follows with a phi to the 4th interaction here. And we see that if S is smaller than this interaction becomes irrelevant. And so we have to take S strictly larger than p over 2. So epsilon will always be positive here. And this is then the non-local part of the interaction, and you can see this as some kind of fractional derivative with the exponent being, again, this parameter s. And because of this non-local interaction, the operators will have protected dimensions. So we will have the operator phi that has conformal dimension p minus s over 2, and we'll have the operator phi cubed, that in this case is not a descendant but itself also a conformal primary, but it also has protected conformal dimension, now given by p plus s. And even if we go to higher orders in epsilon, these will not receive any corrections.
Is the integral for tau 1 goes tau 2 is it conversion?
I think so, yes. Yeah.
It's divisions.
So, I mean, sorry, why would you say it's...
You have a denominator distance between these two fields in the power, which matches dimension of the space-time. So even for s equal to 0, these are already logarithmic singularity at short distances. And if you increase it higher, it's very badly behaving at short distances. The tau 1 goes to tau 2.
Mm-hmm.
Just look at the denominator. I just look at
Yes, yeah, no, I agree. But okay, so this is it is a non-local interaction. But I would say that this is that the integral is.
If it's properly interpreted as a distribution, it's fine. It needs to be interpreted properly, and then yeah, I agree. It probably diverges.
Yeah. So I mean, so for me, this integral would be the definition of taking d phi, but now to some fractional power, which is this parameter s. So this is kind of the interaction that you would have from this term in the action.
It's a Ritz derivative or something like that.
Hmm?
It's a fractional derivative.
Yeah, exactly. It's a fractional derivative of the field. Yeah.
Okay.
So that is what defines this. Yeah, the non-locality of the theory itself. Yeah. Okay. So from the other end, we don't start from free theory, but we can start from a different point of view, which is the initially thought to be the short-range Ising model. But it turns out that it's actually the short-range Ising model coupled to a generalized free field. And here in this case we start from some value S star that is given by this formula here, and we can perturb it for small delta. So from this end we would do conformal perturbation theory, and we see that we have a similar non-local interaction, but now to the power of p minus s, and we have to add the interaction of the short-range Ising model plus a term that couples the Ising field, spin field sigma, to the generalized free field chi.
And you expect this to be a massless theory, to be a gapless theory, or I did not understand. It's critical model, or
yeah, exactly. So for each value of S, this should correspond to a critical point and a CFT. Yeah. And so the claim is also that these two descriptions, you can do perturbation theory from both ends of the spectrum, but they should describe the same CFTs. So also later on, when we're gonna do numerics, I will we have comparison with both ends of the perturbative spectrum, but there should be some or results should be valid along all the range of S. So in this case, also the two operators do not renormalize and are given by these fixed values for each power of delta that we do perturbation theory in.
What is small delta on the right, the first line?
Yes, so this is the small parameter that we would perturb around. So here we have epsilon, and you would kind of do epsilon expansion, and there you do conformal perturbation theory in delta.
So when delta is 0, the theory that you have is decoupled. Basically.
Exactly, it's the short-range Ising model plus a decoupled free theory. Yeah.
But you turn on delta, you flow to the IR, and you find some interesting.
Exactly. Yeah. So then this term becomes couples the two theories together. Okay. So here's a pictorial view of the two pictures that I just showed you, where on these horizontal axes we have written the parameter s, or this picture I've taken from this paper here, and we can start either on the mean field theory side, or we can start where we then flow by a phi to the fourth interaction to our line of critical points, or we can start on the other hand with the short-range Ising and coupled to a free field, and we can flow by sigma dot chi. Okay, so in order to derive certain relations that we want to use later on, there is another picture that has proven to be very useful, and that is the picture of the long-range Ising as a defect CFT. So defect CFTs are inherently non-local theories, and also this point of view of viewing it as a defect CFT embedded in some higher dimensional free bulk theory is a standard way of thinking about generalized free theories. And since those are kind of the starting points of our of the two ends, perturbative ends, it makes sense to think about this picture. So in this case, we define the long-range Ising model and all the interactions to be localized on this p-dimensional defect that lives in a d-dimensional free bulk theory with codimension 2 plus or minus s. So the long-range Ising has integer dimensions, but the codimensions can now be arbitrary and non-integer in general. And we have this extra condition that a bulk field phi is a free field and has to obey these equations of motion.
Question?
Yes.
So at some point you briefly mentioned the potential physical realization. What values for P and Q or S would that be?
So what I believe is that this is mostly P equals to, they look mostly at P equals to 2 around the short range end. But I think for the values of S, I'm not sure if you can have, if there's like a strict restriction. But for example, also most Monte Carlo studies focus on this, the short range end around S equals roughly 2.
equals 2 and D equals 2 then? Or, no, wait.
Yeah, D equals slightly higher than 2 in this setup. But here, let me emphasize that this setup, the bulk theory that envelops the defect CFT, is purely a construct. So it's not a physical thing in itself. So
it's not a short-range theory, the bulk theory?
No, exactly. So the bulk is some free theory in higher dimensions, and for each value of S you can make this construction. So it's independent of whatever perturbation theory or conformal bootstrap you would do. So if we take a defect or a conformal defect in a conformal field theory, if it's free or not, then in general this will break the conformal symmetry of the bulk, and it will preserve, if it's a conformal defect, the conformal group SOP plus 1, 1 on the defect, and also the rotations around the defect. So this is this additional SOQ symmetry. And this means that operators on the defect can also be charged under the symmetry and can have something that's called transfer spin that we will denote by S. And in addition, normally in CFTs, one-point functions of operators are prohibited by conformal symmetry and have to be 0. But in the presence of a defect, they can acquire non-zero one-point functions. And they are given by this one-point function coefficient, A phi, that we will see a lot later on. And for notation, I use these double brackets here to indicate the one-point function in the presence of the defect. So we know that in CFTs we can use the usual OPE to bring two operators together and expand them in an infinite sum of local operators with these OPE coefficients lambda ijk. But now that we have the defect present, there's an additional OPE that we can take. And this is called the bulk to defect OPE, where we take a bulk field phi and expand it in an infinite series of fields localized on the defect. That will be these defect modes psi s. So they can have, in general, transfer spin. And I will denote all the defect operators with a hat to distinguish them from the bulk operators. And these also come with some bulk to defect OPE coefficients B and some fixed kinematical dependence on the distance between the operators and the defect. So now it turns out that since we have a free bulk field, we can apply the equations of motions on phi and find very restricting constraints for the dimensions of these defect modes. So it turns out there's only two types, the plus and minus mode, and each type will have fixed conformal dimension coming from this constraint. And these are exactly these non-renormalization theorems that we saw before in our coming from the non-locality of the long-range Ising model. And in particular, we see that these psi's plus and minus form a shadow pair for any value of S. However, as I said, the long-range Ising is, in some sense, it's not a defect theory, it's a non-local theory. And hence, we shouldn't have this transfer spin, so it doesn't have rotations around itself. So we should only allow operators that have S equals to 0. And this means that in the mean field theory, we now have psi plus that we can, with S equals 0, that we can identify as our phi, and psi minus that we can identify as our phi cubed. And for the short range Ising, it's the other way around. And we have psi plus that is identified with chi, and psi minus that is identified with sigma. And these then give you a relation between their dimensions that could also be seen from the perturbative setup that we had before. So now the goal is to find a set of conformal data, or as much of this set as possible, for the long-range Ising model. So this consists of the conformal dimensions of operators, their spins, and the OPE coefficients of their 3-point functions. And we can either use perturbative methods or the conformal bootstrap to compute or find bounds on this data. So in our setup, we have interactions localized on the defect, and this leads to relations between the OPE coefficients that we can then use to ease our goal of constraining this conformal data. And they turn out to be both very powerful constraints on the numerics, but also let us gain an order in perturbation theory. And I will show both right now. But first, let me show you briefly where these OPE relations come from. There's different ways in the literature to derive them, but we'll follow the approach of this paper, where they started with a defect in free theory, and they looked at the 3-point function between the free bulk field and two defect modes or defect fields that are left unspecified. So we can call them O and T. And we can now use the bulk to defect OPE to decompose phi into the defect modes plus and minus. And now we can write an expression for this correlator, and we can require that it has the right analyticity properties. And it turns out that that's not satisfied trivially, but that you actually need to impose relations between OPE coefficients to make sure that it's analytic in all the right regions. And this leads to the following equation for the ratio of OPE coefficients involving psi minus and psi plus. And we see that it depends on, of course, the dimension of the defect, the codimension, and the conformal dimensions of the two external operators, but also on this ratio R A phi squared that is given by the bulk to defect OPE coefficients. And here A phi squared is exactly the 1-point function coefficient of phi squared. So these are the OPE relations that we will later on use to implement in the numerics and also in our perturbative setup.
Was this for any O and T?
Yes, exactly. I think O has to be a scalar and T has to be a symmetric traceless tensor, but for any defect field.
Psi plus and psi minus is one of shadow of another, right?
Exactly, yeah.
So this follows from the relation between operators.
Yeah, exactly, yeah. So now we can take the second operator to be another plus or minus mode and find two different ratios between them. So this is just from plugging in these operators in the expressions we had before. And we can actually write this R A phi squared that is defined in this way in terms of the actual 1-point function coefficient, and hence find a relation between the bulk to defect coefficients and the 1-point function coefficient. And this can be done from the defect bootstrap, looking at a 2-point function of two free fields in the bulk. I will not show you how that is done, but this is the relation that you eventually get. So we now have formulas that allow us to relate the OPE coefficients of operators on the defect with the conformal dimension of these operators and the 1-point function of a bulk field phi squared.
Is it obvious it's positive?
Sorry?
This expression, it's obvious it's positive?
This expression?
No, the last one. The last one.
This one?
You know, you have expression on left-hand side, something positive, right?
Yeah, so here I just used...
Yeah, but my question is, you have explicit formula which involves some unknown parameter, A phi squared.
Yes.
So then if it's positive, it would mean that some restrictions on this parameter.
Yeah, exactly. So A phi squared has to be positive. Yeah, I think, okay, I have some, in the very end, I have a plot of what values A phi squared can take. This is constrained by the fact that it has to be a unitary CFT. So this, coming from this this 2-point function, if you would derive this relation from there, you also find some constraints on A phi squared. Yeah. As I said, we can use them to gain an order in perturbation theory. So let's now start from the mean field theory end, to pick one. And let's take the third operator that we haven't specified before to be phi squared. Now, we see that because of the structure of the gamma functions, if we plug in the values for p and q in terms of this small parameter epsilon, we see that on the right-hand side we will get a factor 1 over epsilon. And this means that if we would plug in, for example, OPE data at order epsilon, this would give us a relation between this ratio r and the conformal dimensions of phi squared at order epsilon squared. So in this way, we can, if we know the OPE coefficients and we can compute them using Feynman diagrams techniques, for example, we can actually extract a phi squared and delta phi squared to one order higher than we started with. And this allows us to find this conformal data, and that is then relatively straightforward computed in perturbation theory. And this data we can then eventually use to compare to the numerical bootstrap and show that that we can find the long-range Ising model. So we can do the exact same thing, but now for the short-range end. So not starting from the mean field theory side, but then we need to use some shadow transformation, and we have to take s to minus s, q to 4 minus q, and we have to swap these conformal dimensions. So then we can define new relations, k1 tilde and k2 tilde, and they are related to the old ones in this way. And now the one-point function coefficient that will parameterize these relations is a chi squared instead of a phi squared. And it also turns out that there's a relation between these two ratios given by this formula. So in this way, if you do some computations, you can always switch from one picture to the other in a very straightforward way. Okay, let's now turn to bootstrapping the long-range Ising model. So here we will, for the moment, forget about the fact that we can have this bulk defect setup, and we will focus on only operators on the defect, so within the long-range Ising model. And typically for the bootstrap, we will use correlation functions of 4 operators to study. And there's 2 things we can do. So one thing is the analytic bootstrap, which we did in our paper for the 2-dimensional long-range Ising model. And using the mean field theory perturbative setup, we were able to extract conformal data up to order epsilon cubed from the mean field theory end. And I will not go into details for this computation. If you want to know, I can always discuss with you afterwards. But this will give us the quite a high order in perturbation theory, and I will show later on how this really improves the predictions with respect to only including order epsilon squared data.
So that's dimension 2, right? So
exactly, this is only in dimension.
Do you expect some local conformal symmetry?
No, since it's a non-local conformal field theory, you wouldn't have any additional Virasoro symmetry, or like 2 dimensions and 3 dimensions in that case is not going to give you a lot of simplification in this case. So the other thing that one can do is the numerical bootstrap, and this we have done in both 2 and 3 dimensions. And here we will study the fixed points for different values of s that will now be parameterized by the value, the conformal dimension of delta phi. So what we want to study is the following set of correlation functions. So we take 2 operators, and then there's 3 different types of 4-point functions that we can have. One with only psi1, one with only psi2, and one with a combination of psi1s and psi2s. And we can decompose these correlators in terms of the conformal blocks that are given by this G here. And so we can write each correlator as a sum of conformal blocks, which are known in 2 and 3 dimensions and completely fixed kinematically. and the product of OPE coefficients in front. And U and V are here the conformal cross ratios that are given in terms of the positions of the operators in this way.
So is there some symmetry which prevents you from having psi1 3 times and psi2 1 time?
Yes. So in general, I think in this case there is probably some constraints from parity that would prevent you from having this. So, I mean, it depends on which operators you choose, but in general, for example, if one operator is charged or has some has a spin or something like that, then you only always have to pick it in these pairs. In our case, we will take psi1 to be phi and psi2 to be phi cubed, and then there's some parity that prevents you from, I think it's parity that prevents you from putting 3 of them and 1 of them.
So it's the Z2 symmetry of the Ising model,
exactly.
which survives when you do this long range.
Exactly, yeah, that is still there, yeah.
If you had 2 singlets, then it would work.
Yeah, exactly. If you would have 2 singlets or uncharged operators in general, then you could also put 4 different operators there.
You mentioned that the setup that you're going to do numerically will be where psi1 is phi and psi2 is phi cubed.
Yes.
So in that case, the Z2 symmetry would not prevent such a correlate, right? You could still have phi, 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 and then phi cubed, and this is still Z2 even.
That is true. That is true.
I think it's just a consistent truncation of the crossing equations. I mean, it's not the full set of crossing equations.
Yeah, okay, in this case you could also consider 3, okay, sure, yeah.
It could make it more constrained, of course. You're not under an obligation to use it, but...
no, indeed, but in this case we could have involved them, we could have added them. Okay, yeah. Okay, so what we now want to do is all of these correlation functions, because of the associativity of the OPE that we use to decompose them here into conformal blocks, they will obey equation that is central in the conformal bootstrap called the crossing equation. So this means that we can take the OPE between operators in 2 different ways. We can either pair 1 and 2 together and 3 and 4, or we can pair 1 and 4 together and the operators 2 and 3. And this gives us some consistency condition that is given pictorially here. And these crossing equations cannot be solved for just any value of the OPE coefficients and the conformal dimensions. So this equation allows you to derive certain bounds on, in our case, we'll derive bounds on the conformal dimensions for the lowest lying operators. And if you would have infinite computing power, of course, you could go to arbitrary high number of operators, but in practice we would have to truncate, and it's mainly the lowest lying operators that we are able to constrain. So for this setup that we chose, and indeed we could have expanded this, but in our case we only took the pair of 2 operators, then you would get 5 different crossing equations that are given here. With these functions, f are now functions of are some combination of the conformal blocks that we had defined before. So this is the setup that we will use to input in our numerics. And if we would do this, then we would not give it any information about the long-range Ising at all. So we want to input something more that we have learned on the way. So first, as I said, we will specify to psi1 and psi2 being phi and phi cubed. And this means that in practice there is only one external dimension that we need to consider and need to take values for, because these 2 are related by this shadow transformation. Now we also want to impose the OPE relations that we have defined before between the OPE coefficients. We will do that for even spin operators, because it turns out that if you look at them for odd spin operators, then they will either give you that everything has to be 0 very trivially, or they force the odd spin operators to have protected conformal dimensions. So since we're not interested in the trivial case, we will then also input that the odd spin operators have to obey this for their conformal dimension. And on top of that, we also know that the operator with spin 1 is not present in the long-range Ising, so we will take this out of the spectrum and not consider it.
So is this a statement for every odd operator that's exchanged in these OPEs?
This conformal dimension?
In this OPE?
Yes, yeah.
Okay.
Yeah.
There are other odd operators in the theory, but
they need to have this protected.
But you can show that since they don't have this protected dimension, they're not exchanged in this OPE.
Yes, exactly. Yeah, yeah. You can also interpret it in that way. Yeah.
So is this some general statement about OPEs of an operator and its shadow? If you do it such a thing that the opposite is.
So in this case, it comes, well, both from that, but also from the fact that we were considering this free bulk field. So the combination of the two will give you this. And I think, yeah, you really need the fact that the bulk is free as well to be able to get these shadow operators in the first place. So I would say it's the combination of these two constraints that forces this.
What's the reason why spin 1 operators are not there?
Sorry?
What's the reason why there is no operator in spin 1?
Yeah, so if I remember correctly, the reason is that there is, if you would allow this spin 1 operator to be there, then there has to be some conserved current present, and that's not the case. So this is not, we don't want this operator in, it's not going to be in the spectrum.
For any n?
No, for n equals 0. Yeah.
But your theory is conformal, so it means that the stress energy tensor is conserved. So it's spin 2.
But it's a non-local theory. So in fact, we will not have a stress tensor there also.
Sorry, so you're saying there is an infinite family of odd spin operators with like integer dimensions?
Yes, yeah. Yeah, so, okay, indeed, this is the odd spin operators that is being exchanged in the OPE of phi and phi cubed. So this is what, yeah, I guess what you said, it follows from the fact that they are a shadow pair of operators and that they have very constrained OPE coefficients, or that makes this this thing happen. So in general, I mean, in general theories, we would not expect at all to have a large number of operators with protected dimension, but in this case, in this OPE, they appear.
In the short-range Ising model, would they appear or not?
No, in the short-range Ising model, you wouldn't have this protected dimension. But also, I mean, in the short-range Ising, you would also not have the protected dimensions of phi and phi cubed. So that is also not present there.
At the short-range point, these operators decouple from the theory.
Yeah, exactly.
So they're all the way until that point, but then at that point the theory splits into two parts. You have with a short-range part which doesn't see these operators, and then if you put in the rest, then you start seeing these operators. But it says nothing about the short-range Ising.
No, exactly. So we can use data from the short-range Ising model for the long-range Ising, but not really the other way around. Yeah.
It's the fact that you have so infinite number of those operators, odd spin, with protected Kane dimension.
Yeah.
Does it mean that you have infinite number of conserved currents in the theory? Because normally the argument for, I don't know, normally the canonical argument is if you protect operators in the theory, if the corresponding operator is conserved, its Kane dimension is protected.
Yeah, I think.
Does it go another way around?
I think in this case, the fact that it's conserved comes from the non-locality, like from the non-local equations of motion. So it has a different source than normally where you would have the protected, the conserved current. So yeah, I wouldn't say that you have this infinite amount of protected current.
Also for the usual higher spin currents, there would be P minus 2, right? And not
Exactly. Yeah.
Minus
Yeah,
2.
they would also have a different value than this one. Yeah.
Thinking of. So again, it should be
the usual high spin currents have dimension d minus 2 plus L, right?
D minus 2 plus L. Yes.
And that would be P minus 2 plus L, but these are P plus L, so they are somewhere else in the spectrum.
So these are like protected operators with, I mean, could you decouple them from the model or not? Would they appear if you do a OP of 2 arbitrary fields or not?
I mean, so I think if you would do the OP of 2 arbitrary fields, so not of phi and phi cubed, they might be there, but then there's also going to be other odd spin operators with arbitrary dimension. I mean, depending on which operators you take. So in that case, especially from a conformal bootstrap point of view, you wouldn't be able to kind of isolate them. But in this OPE, it's very nice that these are the only odd spin operators that appear. Okay, and then if we input everything, we can write the crossing equation in this form so that it's a single equation, and it's the important part is that this is the equation that's then ready to be put into the numerics, and we can derive some bounds on the first few operators that appear in the spectrum. So let me show you some results first for the two-dimensional long-range Ising, and here we have the bounds on the first spin 0 operator, so the first scalar operator, and we have them as a function of a phi squared. So what we have chosen to do is to use to not fix this a phi squared, but instead use it as a parameter to parameterize these OPE relations, and this allows us to input all of them at once instead of having to restrict to only a few of them. And furthermore, we also show the bounds for different values of delta phi, and these correspond to different values of S, so different fixed points on this line of fixed points. And here the bound is given here, and the shaded regions is what is allowed by this crossing equation and by the numeric. So everything is in white is already disallowed, and we've also put in that the first operator in the spin 2 sector has to start at a certain dimension. So we've put a gap in the spectrum that ranges from 2.4 for this very narrow band to 2.2 for this wider region. And this is mostly for aesthetic reasons. We could have put them at 2.1 or some lower value, and then at least the features that we see would have been the same, just the regions would be a bit broader. So the feature that we see is that there's some kinks, some discontinuities appearing on these bounds. And in general, in the conformal bootstrap, this indicates that these kinks, that there's some conformal field theory that is living exactly on these kinks. So we want to see if these indeed correspond to the long-range Ising model, which we then would expect. So we can compare it to, for example, perturbative data from the mean field theory site, and that is exactly this black line here. So this is for up to order epsilon cubed perturbative results for different values of epsilon, and this black dot corresponds to epsilon equals 0.3. And we see that it indeed coincides very nicely with the numerics and with the kinks that we find.
Sorry, could you remind us where the parameter S enters in this approach?
So in this case, it enters in the value of delta phi. So for different values of the conformal dimension of phi, that would correspond to different fixed points of the long-range Ising. So here, when delta phi is 0.425, it's S is close to P over 2. So this is in the mean field theory region, while in this case, phi is smaller, and it would correspond to S being larger, closer to the short-range Ising end.
So what is epsilon in that case, in the green one?
So this black dot is for epsilon equals 0.3, and that's also the green region. So now I explained that these kinks are normally an indication for the CFTs, but for each of these values we actually see two of them, while we were only looking for one long-range Ising model. So the question is, which one is actually the right one to look at? And for this, what we did is we varied this gap in the spin-2 sector. So this plot is the same plot as before, but now zoomed in on this light blue region. And we have varied the gap for different values of delta 2. And what we see is that the leftmost kink is actually moving as we vary this gap. So this indicates that the long-range Ising model corresponds to the rightmost kink, while the leftmost kink should be something else. And this also says that there is some critical value for the spin-2 gap, for which these two kinks eventually will coincide, and there's only one left. So now let us make another comparison with perturbation theory. So here these x's are the rightmost kinks that we saw from the plots for different precision. And these blue and red lines are the Faddeev approximants coming from perturbation theory. So in blue, we see the Faddeev approximant where we used up to order epsilon cubed data from the mean field theory and up to order delta data from the conformal perturbation theory at the short-range Ising side. And in red, it's the same, but now without the order epsilon cubed data. So you see that computing this one extra order in perturbation theory using this analytical bootstrap that I only mentioned in words really improves the values that we can get. And each of these dots here would then correspond, would have the same value for delta phi as one of these x's coming from the numerics.
To get those curves, do you use the particular data from both sides? Or?
Exactly. Yeah, it's a two-sided Faddeev approximant that we have used here.
Is this on the side corresponding to a short range Ising model is on the left and the GFN is on the right?
Yeah, exactly. Yeah.
So it looks like somehow it works much better on the side of the short range Ising model and not so well on the
yeah, so
what's your intuition? Basically, it looks like
I
the
think
approximation breaks down in the region where it should work the best, which is the GF.
Yeah, so what you can see is that this difference with including the order epsilon cube data really shows up here and is much less important on the short range Ising end, as you would expect. I think like the thing that we have used for the conformal perturbation theory is order delta, and it might indicate that you would need to go to, like, going to higher orders in delta is actually important to match better to the numerics. Hence, that in the area of the short range Ising model, it agrees quite well with these kinks that we found, and here it gets shifted a bit. So a phi squared or a phi squared seems to be kind of sensitive to the conformal perturbation theory order. Yes.
A few questions.
Yeah.
So first, there is a like one-to-one relation between this a phi square and the parameter s. So as you move across this picture, it's like s increases or decreases.
Yeah, indeed. So the relation, the relation is actually with delta phi, but then you can say, okay, you can show that for each delta phi there's going to be one value of a phi squared that would correspond to, that would be valid for the long range Ising model. And indeed, a phi squared equals 0 is then close to the mean field theory end, where you kind of have mean field theory, then that would correspond to exactly a phi squared equals 0. And on the other hand, a short range Ising end, you would have a chi squared equals 0. And using these OP relations and these shadow transformations, you can find an exact relation between a chi squared and a phi squared. That gives you this value here then.
And it's monotonic?
No, that is no.
No, but they
No, so that's not the case. So you can also see. Sorry, what?
I'm just wondering how you did this one here, because the perturbative data is in S, right?
Yeah, exactly. But you can also find a perturbative value for a phi squared that corresponds to.
And then you plug that back in and then get the perturbative value for delta 0.
Let me see. So okay, so the value for delta phi, depending. So delta phi is given by P and S. So for each value of S, you will have a value of delta phi. And then you can also, from each side of the perturbative ends, you can also find a value of S, either P over 2 plus epsilon over 2, or this P minus delta sigma minus delta. So this also gives you a value for S. And then you can find a value for a phi squared. I can actually show you here where we computed this in perturbation theory. That would give you, so for each value of epsilon, you can extract this a phi squared.
But only for small epsilon.
Well, if you do the Padé approximant, you can
So you do a Padé approximant for a phi square in terms of epsilon first, or?
So I mean the Padé approximant curve is for the value is for delta 0 and a phi squared. So for each value of epsilon or delta, you know the value of delta phi. That is not like a perturbative statement, that's exact. And you can compute the perturbative, you can compute the perturbative results for these two parameters. So you have an expression in terms of epsilon and an expression in terms of delta, and then you force them to match along different values of S. And then you say, okay, from that I can do my Padé approximation.
It's a parametric plot in terms of S.
Yeah, exactly.
But in principle, it could swirl back and make a loop. If you say a phi square is not monotonic in S.
In that sense, you mean? Okay.
It doesn't matter. But
okay, sorry, yeah, I think I said it wrong. Then it should be monotonic in S because it's not swirling back, but it's really interpolating between roughly minus 0.8 and 0 on the other side. Yeah.
Okay, cool, thanks.
Okay, now one open question is what this leftmost kink would actually correspond to. And one idea that was already observed in a previous paper was that it could be coming from a GFF coupled to a minimal model instead of the short-range Ising model. So in principle, nothing prohibits you from making such a construction, and it would also lead to a non-local model that could be picked up by the numerics. But then, of course, for different values than the short-range Ising model.
Sorry, so do you mean you could couple the GFF to actually any unitary CFT and obtain a generalization of the
okay, yeah, you would have to see if this would actually lead to a valid infrared fixed point, of course. But at first sight, you could, so with the minimal models, in the case of a boundary, these constructions have been made. In the case of boundary CFTs. And in this case, the motivation of this is not just, okay, this is something you could do and this might explain it. But if you would actually look at the short-range Ising n, so for a chi-squared is 0 and the corresponding value of a phi squared, then we find that the bound on this delta 0 is given in terms of delta phi in this way. And this is exactly the relation between two conformal primaries, these two conformal primaries in the M-sphere-Zorro minimal model. But at this point, this is an observation that we made, but we haven't actually constructed the model and done any computations for this. So this is something that we would like to further look into. But at this point, this is the observation that we found this relation, and I will show you in a minute some further support for this idea as well.
And then you have an extra parameter, which is this m. How do you fix the value of m?
Yeah, so in this case, so you can also see that this leftmost kink was the kink that was moving around. So this also seems to indicate that you would also expect some other parameter that you could vary. And at this point, I don't know which ranges for which values of m this would be a valid construction that you could do. That would be something to look into when we actually do the construction and the computations. But these plots already indicate that you would have some additional parameter that you might move around.
Okay, but would you want your CFT to be unitary or not?
Yes, exactly. Yeah.
Because then you would have to take m to have some discrete values.
Yes. Yeah. Yeah. But I don't know at this point. So we haven't done the construction for which values of m you would get what kind of behavior. So that I cannot. I don't know.
Yeah. But am I right that there would also be a natural guess what is known as the CFT should be on the opposite side, where it basically comes from some GFF, but deformed not by phi to the 4, but phi to some higher power.
Could be. Yeah, that could be. That's actually we haven't thought about, but that would be. Yeah.
I think a long time ago people looked for this Ising model coupled to Liouville.
Ah, okay, yeah.
And there is an exact formula for scaling dimension.
Okay. Okay. I didn't know about that, but yeah, that would be that would also be very interesting too.
Then also you have exact formula, KPZ formula.
Yeah, so then there's nothing left to.
In principle, your results should be consistent with that formula.
Okay. Yeah.
Because this give you bounds, right?
Yes,
events
exactly.
for deltas.
Yeah. Yeah, I see. So okay, so you mean that maybe this other kink, or even in general the bounds, we should be able to identify these.
I don't know, but at least there's some point which would. There's some point which you could put on this plot. It should be living within your region, and the question is whether this is the corner or not.
Yeah.
But at least there is some exact value.
Okay. Okay, that would be interesting to look at. Yes. Okay, I see that I have to speed up a little bit, but so let me just show you one last comparison, and now not with perturbation theory data, but with Monte Carlo simulations. So there have been Monte Carlo simulations by two different groups, which are the most recent results, that have shown some discrepancy between them. And one of our motivations was to see if the conformal bootstrap would actually be able to favor one of the two instead of the other. And these simulations are done around the short range n, so for delta phi equals 0.2, that is the shaded region here. And for these other values, the kinks are given by the crosses. And we see that the kink is slightly above these results from Pico, but well within the region of results for this group. But of course, if we really want to say that we can exclude one of the two, we should find some island instead of only a kink that would truly exclude this region for the Monte Carlo results. So we tried this. We slightly changed our approach, and we also increased the gap in the spin2 sector to get more restraining bounds, and we now also are able to find a lower bound on this delta zero. So for these values of the spin2 gap, the allowed region of these parameters is really constrained in these islands. But the problem is that you can see if you would push the value of delta 2 too high, that at some point you're excluding the long-range Ising model or the kink that we saw in the numerics, which is here. So, and for the island that we get that does include this kink, we can still not exclude any of the Monte Carlo results. So if we want to do that, we should think of a different way to push the numerics, except just increasing this spin2 gap. Now, yes?
Did you have a perturbative prediction for this dimension of the spin2?
Yes. And I can look it up afterwards for you. I don't know, I forgot it, but yeah, I mean it should be somewhere around this value, but not not too far off from this. So the numerical bootstrap for in 3 dimensions is slightly harder than in 2 dimensions because the 2 perturbative regimes overlap less well. So you would have to go to higher orders in perturbation theory to get proper predictions. And also the perturbative results at the short range end do not match the numerics very well unless you really go very close to the short range values of delta phi. But what we also see is that the bounds that we get, they do not move after imposing a spin2 gap, and we only find a single kink, which we can see here, which is furthermore some support for this idea that the second kink was given by a coupling to the minimal models because they have upper critical dimensions below d equals to 3. So here are some of the results that we get. Again, we put a bound on the scalar operator as in terms of a phi squared, and we see that we get these nice kinks for different values of delta phi. Okay. How many minutes do I have?
Maybe 5.
5? Okay, perfect. Then let me comment on the 1D case. Of course, we could do the analytical bootstrap and the numerics in 1D as well, and we could also impose these OPE relations, but and even use additional techniques for the conformal bootstrap, like analytic functionals. However, it's not clear what the short-range Ising end is in 1D, because the short-range Ising model itself doesn't exist in 1 dimension, so it's not clear what this crossover between the mean field theory and the other end would entail. And there's some ideas for what this could be, and there's some models that have been written down, but no consistent continuum description that you could use to do perturbation theory in. So before tackling this model, you would really need to know how to interpret this other side of the perturbative spectrum. Then, okay, you could also generalize this whole setup to include ON symmetry instead of the Z2 of the Ising model. And the nice thing here is that now it is known what this would correspond to in 1D. So this would be a nice starting point in 1 dimension, maybe to study these types of models. But unfortunately, if you would then put n equals to 1, then everything diverges and you end up again with not knowing what to do. Okay, so some direct further outlook that we could do is further push the numerics to try to create these islands to exclude the Monte Carlo results, and also extract some data from the kinks and further compare it to perturbative results that we already have. Then we could extend it to look at the 1D or maybe long-range ON models. And we should also further investigate this coupling to the minimal models in 2 dimensions. And I think more generally, this has shown that these OPE relations really allow you to do a lot of stuff. So to either push the numerics a lot further and to find really nice kinks and good constraints, but also on the perturbative side to get some advantage there. And it would be nice to look at other types of these setups where the interactions are localized on the defect and you would have some free bulk theory. Examples are monodromy defects in free theory, in 4 dimensions, for example. But there's many more setups that one could consider. And yeah, I hope that this study has kind of proven that this is a very nice way of looking further into non-local CFTs and models. So thank you.
Any questions in the talk? Somebody has a short question. Okay, then thank you very much. Will you have lunch with us?
Yeah, I would love to. Yeah.